No? Yes? Okay. Yeah, so as you recall, what we said last time is that we want to explore the relationship between optimization, in particular what I described as the geometry of optimization, and generalization or learning, and also between the optimization algorithm and the implicit biases. And so what we're going to do today is actually not directly answering the questions we really pose about understanding this for all these non-convex models, but looking at it in a situation which we do understand it pretty well, which is in a convex setting. So in a convex setting, we have, or we thought at least we had until recently, a pretty mature understanding of the relationship between optimization and learning, and how the optimization geometry gives us generalization guarantees. And much of what we'll do is not directly applicable, actually, I think, in a non-convex setting, but I still think it's important to see the convex setting first, both because it does give us, it does show us the type of relationship we can get, and also because it'll help us derive at least what my view of when I think of the optimization geometry, in particular the mirror descent algorithm that I think we took a poll last time and most of you are not familiar with. And so in some sense, about half the goal of this lecture is to understand mirror descent and get some intuitive, we'll see several different intuitive understanding of it. I also want to apologize. I didn't actually finish preparing the lecture because it was supposed to be tomorrow. It's mostly ready, but there is a bit of glitches. In particular, the color scheme, as you'll see, will switch on you in the middle. I hope it's not going to confuse you too much. Okay. So where are we? So we want to understand the relationship of optimization and learning, and we called it. The goal of learning is to minimize this expected loss. That's how we defined learning last time based on a sample. And one particular way of doing it is essentially by solving an empirical optimization problem. So we collect our samples and then we minimize the empirical loss. Oops, where is it? I'm missing where's my lambda here? Oh, I erased it. Okay, sorry. As I said, there's some glitches in the presentation. So what this should say is plus lambda times psi of, write it here. So we want to solve this minimization problem of minimizing the empirical loss, which will denote LSW plus lambda times some complexity, what we called last time a complexity term. Okay, so. And this is our optimization problem. So for a lot of the looking at machine learning, we kind of think of using optimization for machine learning. We want to solve this machine learning problem. In order to do that, to implement the rule, we use optimization. And then the optimization has nothing to do with kind of generalization or statistics. It's just implementing this argument. And then we're going to argue for generalization, say using uniform convergence inside these sublevel sets of psi, by saying we have small capacity. So let's see how this works out for a particular example. So suppose what we want to learn is the class of low norm linear predictors. Okay, so this is our if you think of it in terms of our complexity measure, so we assume that reality is captured by some linear predictor, and we expect the norm to be small, and so we want to sort of find a particular small norm, or here I'm taking it to be just bounded norm. Right? So the empirical optimization problem we want to find, we want to solve is just minimizing this empirical error over a bounded, in this case, let's say it's explicitly a bounded Euclidean norm set, and then we can use the capacity of predictors of norm at most b, and we know that's bounded by b squared, and so we know that we have, for all the predictors of norm at most b, the empirical error and the expected error differ by at most something like square root b squared over m, where m is the number of samples, and we can conclude that if we do solve our empirical optimization problem, our learned predictor will be only square root b squared over m, worse than the best predictor in the class. Okay? And now the question is just how do we solve this optimization problem, so we can do it by gradient descent. And now we need, so gradient descent, hopefully you don't need to do this. In each iteration, we just take the current iterate and subtract the gradient of our empirical loss from it with some step size eta. And now we just have to ask, okay, how many iterations of this will we need? Okay, so what do we mean? We need, okay, gradient descent will never actually find the optimum. We only get like epsilon close to the optimum. We can ask, how many iterations do we need to get epsilon close to the optimum, or the way we're writing it here, after t iterations, right, how close to the optimum will be. And what we can say is that the guarantee for gradient descent ensures us that for an objective of this form, objective that's in this case Lipschitz over the set of over this unit Euclidean ball, the number of iterations we need also behaves as square root b squared over t. Okay, so now this is what we can do with gradient descent. With gradient descent, at each iteration we have to do a kind of to consider our entire training set, because to calculate the gradient of, oh my god, this is even worse than to calculate the gradient of this objective, I have to sum over all m training points and calculate the gradient of each one. Okay, so that means that the number of, the amount of work per iteration scales with number of examples. It turns out that we can do much better than that. Instead of using gradient descent, we can use stochastic gradient descent. So for stochastic gradient descent, which you've all also seen, there are two, operationally what we do for stochastic gradient descent, each iteration we only use a single example out of our training example. So here we're doing stochastic gradient descent as an optimization method to optimize our training objective. At each iteration we pick a single example xi, yi at random from our m examples, okay, and calculate the gradient only on that example. Formally what's going on here is that instead of using the exact gradient each iteration, we're using an unbiased estimator for the gradient. Okay, so we're using the, okay, there's a nubla missing here also. We're using the gradient calculated in a single example, and the main property we want is in expectation over this choice of random example from our training set. This actually gives us the true gradient that we want, the gradient of the empirical error. Okay, and now what we have so far is two separate guarantees. We have a cell optimality guarantee. So this tells us out of t iterations of optimization how close we would be to the empirical optimum. And we have a separate guarantee that tells us for the empirical optimum, how far are we in terms of, we find it to minimize the empirical objective, how good are we in terms of the population objective. So this L is the population objective. Okay? And to get a guarantee for our entire learning method, so if our learning procedure is actually running gradient descent for a finite number of iterations, we need to add them, both of them together. And we can get this combined guarantee, which is that tells us that the population error, expected error of the result of gradient descent after t iterations is bounded by the best we can do in the class, the best with best error achieved by any linear predictor of norm at most b, plus this estimation error term, okay, squared b squared over m, and that term bounds the variation due to the fact that we're only optimizing over a sample of m points, and an optimization term, which results from the fact that we're only optimizing for t iterations. Okay, so for this view now we can just ask, okay, how many samples do we need and how many iterations we need? And we can see that in order to get both of these to be small, we need to get the number of iterations and the number of samples to be roughly the same, right? So there's no point in, if I want to get be epsilon close to the best possible in the class, I need both of these terms to be about epsilon. Okay? And so I need both m, the number of samples, to be roughly b squared over epsilon squared, and the number of iterations to also be roughly b squared over epsilon squared. Okay? And so this tells us that in some sense doing, so taking this view, we already see a sort of connection between optimization and learning, that somehow the complexity of the optimization problem we're solving is sort of strangely the same as the complexity of the learning problem. meaning the number of samples that I need, the number of iterations that I need are about the same. Okay? So this also, so in other words, another way to think about it is, if I have m samples, how many iterations of SGD do I need? There's not much point in doing much more than m iterations of SGD, because after m iterations of SGD, both of these error terms, if t is equal to m, both of the error terms are about the same. If I continue doing more iterations of SGD, I'm going to decrease this error term, but this one will become dominant and I'm not going to win much. Okay? Right. So, yes?
So how's the gradient descent enforcing the norm?
Okay, good question. So I can, the way it's written there, okay. So, right, so if I want to, okay, so excellent question. So if I actually want to solve this optimization problem as written here, which based on the view I took so far, I should do. So what I should actually do is projected gradient descent, which means that after each iteration of gradient descent, I also have to project back to this norm ball. Okay? So, right, so that's not written there. So WK plus 1 is actually the previous iterate minus the gradient, and then normalized, if the norm of that is greater than b, I normalize back to have norm b. Okay? Should I'm going through this a bit quickly because I'm assuming most of you have seen this, and what I want to do in a bit is actually show how we get these guarantees. But should I write projected gradient descent on the board, or is that clear? Oh, yeah, okay. Question?
So what is t here? Like,
so t is, no, there's no gradient flow here. Everything is discrete time, so t is the number of iterations of gradient descent.
But that would then depend on the learning rate.
Okay, so I have to choose the learning rate. Okay, so it's a good point. So this is what I can get with the optimal learning rate. Okay, so, okay. Okay, so this is sort of one way of kind of linking optimization and learning already that we see that the sort of the number of iterations of the runtime of optimization is similar to the runtime of learning. But actually, we can take a step beyond that. Okay? What we did here, the view we took here, is that we're running stochastic gradient descent as an optimization procedure on the empirical objective. Okay? Right? So from the perspective of stochastic gradient descent, the objective is this empirical objective. But alternatively, what we can do is you can also think of the objective for stochastic gradient descent as the actual population objective, what we actually care about, right? So the actual expected loss on a population. Okay? So the thing is that this is really what we care about in learning, right? We want to minimize this expected loss. And the problem is that we can't actually calculate it, right? I don't know what the population error of W is. But the thing is that for executing stochastic gradient descent, I don't actually need to know what the population loss is. I don't need to know what the objective is. All I need to do is be able to find unbiased estimators of the gradient of the objective. I don't actually need to know what the objective is. And that we can do. Because every example, if we take an example xi, yi drawn from the population, then the gradient calculated in that example is an unbiased estimator for the population gradient, right? Because so we have, right, that's right, because since the population loss W is exactly the expectation over all these examples of the loss on the example, right? If I look at the gradient of this loss, can take the gradient outside the expectation, and I get that the expectation of the gradient is exactly the gradient of the expected loss. So that means that we can actually view stochastic gradient descent as directly optimizing the population objective. We don't have to go through this two-step approach of separately analyzing the optimization error and the generalization error. And we can actually once we do this, the optimization guarantee we get for stochastic gradient descent is directly on the optimization objective, which in this case is the population error. So we get directly, the stochastic gradient descent guarantee itself already directly gives us a learning guarantee. Directly gives us a guarantee on the population error, and we do not have to go through uniform convergence. Okay? Okay, so in the important thing here is that for this to be valid, we need all our stochastic gradient estimates to be independent, and so we need all the data points xi, yi that we use to calculate unbiased estimators of the gradient to be independent of each other. Okay, so in other words, we can only use each data point once. Okay, we'll see this maybe more. We'll see this again in a second, but let's just think about it for a second of what we did here. So we started with thinking about optimization as a way of solving a learning problem, a way of implementing a learning rule. But then what we saw is that actually we can phrase learning itself as an optimization problem, right? And then apply stochastic optimization directly for stochastic optimization methods directly to it. Okay, so let's formalize that a bit more. So the type of problem we're solving here is a stochastic optimization problem, right? Where what we have is an objective, which is an expectation with respect to an unknown distribution, okay? And we want to minimize this expectation. So we have our optimization objective is some function f of x, which is an expectation with respect to some latent z of some known function f of x and z. We don't know the distribution over the z's, okay? And we don't have direct access to our optimization objective. All we have is access to unbiased estimators of maybe f, or more importantly, the gradients of f. Okay, so for example, we can get that if we have access to sampling from the distribution d. Okay, and so what? So this is a general formulation of the stochastic optimization problem, and what we saw is that we can actually formalize learning as a stochastic optimization problem. So learning is in this case, just a special case of a stochastic optimization problem, where our optimization objective is a mapping from x to y. Right? We said that we're talking about learning as supervised learning, as learning a predictor. Okay? And what we want to find, we said in learning, is just to find a predictor with good expected error. Okay? What's the expected error? Just the expectation over samples x and y from reality, from the source, from the population, from the source distribution, of the loss that our prediction would make. Okay, and we want to do that based on these on samples from population. Okay? And so this is exactly a stochastic optimization problem where our optimization objective is this is our instantaneous our loss on an example. Okay? And in fact, we're saying here that learning is a special case of stochastic optimization. You can also think about more general forms of learning. So Vapnik actually, in his book, actually talks about general learning setting, where instead of having predictors from x to y, you have a general object h and a general loss function over that object and over samples from z. And this is exactly up to a change of notation exactly the same as the stochastic optimization setting that's studied in optimization literature. So the variable names in this slide might be a bit confusing, right? Because we're using x here. So in the top of the slides, I started using x for the optimization variable, and up until now, and actually in all the other slides, I'm actually using x for the input to the function, and here our optimization variable is actually h, our predictor that we may characterize by w. But this confusion about the different, how we call the optimization variable is basically the only difference in some, formally between stochastic optimization and learning. Okay? And so formally they're the same setup. Actually, I'm going to show a few more examples of stochastic optimization, but I see some glazed looks, and I realize maybe this was not. I'm now realizing maybe I hope I'm not even less prepared than I thought I was. Is the picture? Is the question so far? Is the picture overall clear of what's going on here? Yeah. Question in the back there? No? Okay.
Can you explain what specifically the term uniform convergence refers to? Like what part of the process is this?
Okay, good question. So we'll actually not be, so part of the point of what we're going to be doing today is we're going to be avoiding talking about uniform convergence. But just to explain what we're not doing, which is important, right? So in the uniform convergence, so just maybe first of all, to answer the question and of what I mean by uniform convergence. So we stated a general, I thought I covered last time, so if you look at a learning rule, the ERM learning rule, which is what I have there. So here the hypothesis class are all the low norm linear predictors. Okay, let's write it as HW, or HW is the linear function with the coefficients W, right? And we're learning using empirical risk minimization. So this is our learning rule here. So our learning rule is W hat is we're minimizing the empirical error over W. And what we really care about is the population error. Okay? So one way to ensure that minimizing the empirical error would actually be good as minimizing the population error is to bound to bound the difference between the population and empirical errors uniformly over all predictors in the class. Okay? If I can bound this, okay, then I can say that so if I can bound this by epsilon, then I can say that the population error of W hat, okay, is at most its empirical error plus epsilon, okay, based on the fact that all the population and empirical errors are close to each other. And in turn, the empirical error of W hat is definitely better than the empirical error of the best, or of any predictor in the class, in particular W star, which is a population minimizer, okay, because I chose W hat to minimize the empirical error. Okay, and the empirical error of W star is in turn close to its population error. Okay? So you can ensure that minimizing the empirical error is within 2 epsilon the same as minimizing the population error. It shows you W star to minimize the population error. So this is a standard approach, and what we get as guarantees that the standard approach is to say that with high probability this would hold. All the predictors in the class, the population error will be close to the empirical error. Okay? And this is what gives rise to this additional term here. Okay? The point is so this would be if we look at the view we took last time, we said where is it? When we restrict to some sublevel set here, then we want to have small capacity, then really the way we use the fact that small capacity is to get this uniform convergence guarantee. And then using uniform convergence, we said that minimizing the empirical error within that sublevel set is close to minimizing the population error, plus a term that would depend on the capacity. Okay, so that's kind of the standard argument. And what we want to do here is actually to avoid the standard argument. Okay, so we avoid that standard argument. We avoid that by actually directly looking at optimization guarantees for this stochastic optimization problem. Okay, good. So maybe now the discussion from the past few minutes was a bit clearer. Okay, still questions? Okay. Sorry, should have started with that. Okay, so what we're going to be talking about today in general is the stochastic optimization problem, where supervised learning is one example of such a stochastic optimization problem. Just to give you a sense of the sort of richness of thinking about stochastic optimization, so beyond supervised learning, so in stochastic optimization in general, we talk about we have an optimization variable that on this slide I call H. We'll generally in this today call it W, and some randomness Z. Okay? So the first example we saw is for supervised learning, with this randomness Z is input-output pairs. H is a predictor from X to Y, and the objective is the loss of predicting H of X when the target is Y. Right? Some other examples, we can also think of it for some unsupervised learning tasks. For example, for k-means clustering. So for k-means clustering, the randomness, there's no labels, right? The randomness is just points in RD. And what you're optimizing is the cluster centers. Okay, so you can think of H as representing the cluster centers. And then your optimization objective for a random point is the distance to its closest center. Okay, so now your population objective would be the expected, you want to think about the stochastic optimization problem, is you want to find centers that minimize the expected distance from a random point to its closest center, and you want to do that based on a finite sample of points. Okay? Or another example is density estimation. So again, this is similar to this unsupervised learning problem in the sense that we only have, there's no labels, there's only, the randomness is only in x's, and now you can think of the hypothesis as specifying some density function, and if you want to find the density that minimizes the KL divergence from population density, then that corresponds to thinking about the objective for any instance z is the negative log probability under your model of z. And so then if you take the expectation with respect to z, you get up to a constant term, the KL divergence between the population and P of H. Okay, so again, here you're trying to, the population problem would be to find a density that's close in KL divergence to this unknown population density, and you're doing it based on a finite sample. Okay? Or another example is routing under uncertainty, okay? Or routing with random traffic patterns. So you can think of, the randomness is you have some map, you can think of it as a graph, and the delays on each edge are random. You don't know what the expected delay on each edge is or how they're correlated. You want to find a route between some source and destination that minimizes the expected delay. Right? And so here H, what you're optimizing is the route, and Z, the randomness is the random traffic delays. Okay? So again, this is another type of stochastic optimization problem. Okay? So stochastic optimization is the background. So stochastic optimization, we said, is equivalent to learning in some sense. So this Vapnik's general notion of learning. It's kind of strange because the two problems were both of them developed in the late 60s or in the 70s, from what I understand, maybe even the same building in Russia, or at least definitely both in Moscow, and really studied very separately. Like so, and only in sort of about 20 years ago, there's been a convergence of looking at optimization and learning as really the same thing, and understanding how we can really should be maybe looking at learning as optimization problem. And this really just stemmed from just different interests of maybe the main people that studied them. Arkady Nemirovsky for stochastic optimization. So stochastic optimization we looked at before, but Arkady Nemirovsky really formalized it and studied the way we will today. And Vapnik that formalized learning. And one difference is what the limiting factor was. So Vapnik was only concerned with the statistical aspect. The limiting factor was only the number of samples, whereas writing an argmin was perfectly fine. I mean, didn't care at all about optimization. Whereas from most people looking at stochastic optimization, including Nemirovsky, most of the emphasis was on efficient computational techniques. So samples, you can think of it as a simulator or something like that. You could have as many samples as you want, and really the emphasis was just on running efficiently. Because of that, Vapnik looked at general combinatorial hypothesis classes where it might be impossible to do the argmin, but it doesn't matter. You can still look at the argmin. Whereas Nemirovsky's theory was mostly for normed vector spaces, which is what we'll look at today. Okay? And because of that, also sort of more specifically in convex objective in normed vector spaces. Okay, so what we'll be looking today, we said we'll be looking at learning, but really we're looking at stochastic optimization in this formulation. Questions? Yes.
In stochastic optimization, stochasticity can arise due to other reasons apart from just sampling from the distribution, right? So it's
Like,
it could be just some random noise in the system, or so it could be just random. Like, and also in learning, if you're talking about samples from a distribution, doesn't that give us like more information?
so I'm not entirely sure what you mean by other. Okay, so again, the formulation here is they have some unknown distribution D. I mean, that unknown distribution includes also any noise or anything else in the system. I'm not sure what you mean by
Like,
other.
That doesn't have to be the data distribution. Like, it could just be an arbitrary distribution.
I guess I'm not sure what you're getting at. I hope
like,
this.
for example, in stochastic optimization, we often assume like that the noise is supposedly IID Gaussian in the gradients. Like that is also like one of the assumptions. But that is not necessarily captured by the learning problem.
So I still am a bit confused on what. Okay, so the thing is that what the way at least we're going to be looking at it is, again, so you have some objective FWZ, and you can think of FWZ as, I think if you want to say that you have, that each sample gives you a gradient plus some Gaussian noise, that would correspond to looking at FWZ as, we write it here. That would correspond to thinking of FWZ as f of W plus some random Gaussian times W. Okay. So if this is so where this is, let's think of this is Z. Okay, where Z is Gaussian. Okay.
But is that captured by learning problem? Because
is that captured by a learning problem? Okay. So again, so supervised. I wouldn't say that it's captured by supervised learning. Okay. So I don't think it's the supervised learning problem as we defined it here. But as we said, we're looking at the what you call a learning problem now is just a matter of what you decide to call. So it does capture by what Vapnik referred to as generalized learning. Okay, so it definitely is. The important thing is captured by this formulation, which is what we're looking at. Does that answer the question? Or? Okay. Okay, so let's start. Let's try to start again, and maybe this time we'll start a bit better. So the problem we're looking at is solving a stochastic optimization problem. And what we kind of saw is we can think of two different approaches of solving a stochastic optimization problem. So if I want to minimize this objective based on the IID sample, I can do it either using this empirical risk minimization approach, which means I calculate the empirical error, okay, and hope that the empirical error is a good surrogate for the expected error, and then minimize the empirical error. Okay. Or I can maybe do something like SGD. And both of these approaches have been studied both in the machine learning community and the optimization community. Again, we studied different names. So what I would call empirical risk minimization is in stochastic optimization is called the sample average approximation approach. Right? So we build a sample average approximation of the objective and minimize it. And a stochastic gradient descent is an example of stochastic approximation. And basically, the stochastic approximation is the way we're going to use the samples each time we're going to use each sample to make a small update to our iterate. Right? So in the optimization algorithm itself, in the same way we did in stochastic gradient descent. Right? We take a sample, we calculate a single stochastic gradient estimate from it and use it to update our iterate. Okay? So the number of, we kind of combine the optimization and the sampling. And so with that in mind, and now we said that if we think about where we started, we think we have a learning problem, and we can either think about using ERM and then optimizing, solving the ERM problem using stochastic gradient descent or using stochastic gradient descent directly, then what we're doing is sort of combining, in some sense, both of these approaches, right? So if we're we can either take the direct stochastic approximation approach, which means that we're viewing our optimization objective as our population objective, viewing our population objective as our optimization objective, and then what we do at each iteration, we sample a point from the population and take a stochastic gradient step on it. Okay? At the end, we have to also, and we'll get back to this later, return instead of the last iterate, we have to return the average iterates, and we'll see in a second why. And what we did when we used the stochastic gradient descent to solve the ERM problem is a bit of a combined approach. We use a stochastic average approximation approach or ERM approach to solve our learning problem, right? So we build an empirical average and then minimize it. But the way we solve this empirical optimization problem is using stochastic approximation here in the form of stochastic gradient descent. Okay, so let's look at so this is the difference between what you might call one-pass SGD or multi-pass SGD. But let's look at how what the differences, how the differences between them look like. So when you're using the stochastic approximation to solve the sample average approximation problem, okay, then you first draw all your samples, right? And we're going to, in our minds at least, build this empirical approximation based on them. But then what we'll do at each iteration is we'll pick only one of these uniformly at random, and then take a stochastic gradient set based on it. Okay? Project back to having small norm, as somebody here reminded us that we should do. I think it was here, right? And then at the end, after t iterations, again, average the iterates. So let's look at the differences between both of these methods. So the main difference, right, is that here we can only use an example once, right? Because we need all our stochastic average, all our gradient estimates to be independent of each other in order for the SGD approach to be valid. Okay? And so the number of iterations is limited by the number of points. Okay? Over here, when we're using stochastic approximation in this mixed approach using stochastic approximation to solve the ERM problem, then the number of iterations and the number of training examples are unrelated. I can take many more iterations than examples, right? I can do a multipass, use a multipass method. Okay? And in order to allow that, the other key difference is here, it is important to project back, right? Because I need to solve my ERM problem inside my hypothesis class. I need to constrain the norm here because my generalization is coming from the fact that I constrained the norm here. Okay? And so I have to include a projection step, whereas if I take the direct approach, I actually don't need to project. Okay? As we'll see, the stochastic gradient descent guarantee is going to be valid even without projecting. Okay? In some sense, and now if you look at the guarantees, we said that to get a guarantee here, I have to combine this statistical guarantee, for example, from the uniform convergence argument we had before, with the optimization guarantee. Okay? Whereas if we get a guarantee, to get a guarantee here, I use the online gradient descent guarantee gives me the stochastic gradient descent guarantee directly gives me a bound on the suboptimality. Now, there's something strange here, okay? Because the guarantee I get here rests on the fact that I'm competing here, so maybe we should write directly what W star is. So W star here is the best we can do in the class. So it's or maybe better to say what f of W, just write what f of W star is. So L of W star is the minimum possible loss I can get for a predictor of bounded norm. Okay? So this is what I want to compete with. And the bigger the norm, it's harder to compete with it, right? So the bigger the norm, I'm going to have more samples or more iterations. Okay? Now, over here, it's pretty clear, okay, how this norm comes in, right? So each time I'm projecting to predictors of norm at most b. So it's pretty clear where the complexity control comes in. Okay, so let's actually go back to the first lecture. We said that in order to learn, we have to have some kind of complexity control, right? We have to control, to on one hand, fit the data well. On the other hand, we have to control the complexity of our predictor. Okay? And so both we need to know, what complexity measure we're controlling and by how much. Here, it's very clear where the complexity control comes in, and also what the knob is that I can turn to change the balance between how well I fit the data and how much complexity I allow. Right? It comes in directly in the projection step. Okay? What happens here? Okay? So this is a bit strange, right? There's no apparent complexity control. In particular, if I'm telling you that I'm getting this guarantee, okay, for any, and I can get this for any W star of norm at most b, okay, how does the algorithm know with which norm b it has to compete with, right? Where is this knob that controls what ball of predictors I want to compete in? What is my hypothesis class? Is the question clear? I feel like I'm okay. So what's going on here? How do I actually, in the direct approach, since I'm not doing a projection step, what's the parameter that actually controls what I'm competing with? Answers? Yes. So the step size, right? So I have to choose the step size. Somebody asked before. I have to choose the step size. So all these guarantees are with optimal step size, and the choice of step size would depend on the norm I want to compete with. If I want to compete with predictors with larger norm, I'd have to use larger step sizes. Okay. Okay. And so this is actually let's skip this. Okay. Yeah.
So in the second case, when you have t smaller than n,
yeah,
seems intuitive that the two guarantees should be similar, but you're getting something much worse.
If I have t that's what? That's
smaller than n.
Right. So if the t is smaller than m, I am indeed getting much worse, which is a real thing, right? So if I have m examples, okay, so if I have 1,000,000 examples, okay, I can either use this approach, okay, and then I can take as many steps as I want. But if I only take, much less than 1,000,000 steps, if I only take 100,000 steps, then this term would become dominant, right? The optimization term here, the b squared over t, would become dominant, which is a real thing. That means that I actually will not be optimizing my empirical objective well enough, and I'm going to suffer large error because I didn't do a good job optimizing.
But somehow you have this extra gap in the guarantee there compared.
Okay. You're worried about the fact that even if t goes to, okay, sorry, I'm not.
If t is less than m, then.
If t is less than m, or if t is, so if t is less than m, I really should be in trouble. Maybe what you should be worried about is what happens when t is much bigger than m.
But if t is smaller than m, isn't it similar to?
If to here? Yes. Yeah, yes. So okay, I see what you mean. Okay, right. So you're saying that shouldn't I be getting, if t is, okay, so all the guarantees here you should only be taking, so that although everything here is written, that is correct in terms of upper bounds with the constant written, you shouldn't be paying too much attention to the constants here. So you should take all these guarantees. All the guarantees are tied up to some constants, not very big constants, but they have constant factors of like around 8 or something like that. Okay, and so you're right. What you're saying is that I get, if I take t to be much less than m, then these two are the same, and somehow here I get this additional term, which is much smaller, but it's still a difference. But since the difference would be less than, say, a factor of 2, then it's just because of looseness of the analysis here, right? So really, you should be attention on what is the dominant term, right? So maybe I'll repeat that because that's a good question. What we can see from here, right, is that we said that with one pass SGD, if I have 1,000,000 examples, I have two options: either to just do one pass SGD with 1,000,000 examples, or to do, and then I can only do 1,000,000 examples, or to take the mixed approach, and then I can take as many iterations as I want. But what we see here is that it doesn't make sense to then take, so if I take 1,000,000 examples, then both of these terms would be the same. And again, up to maybe a factor of 3, the guarantee I would get with one pass or with 1,000,000 iterations over a sample of size 1,000,000 would be the same. Okay? The other option is to take much fewer steps. I have 1,000,000 examples, but I only take 100,000 steps. In that case, what I'll be dominated, even though I have 1,000,000 examples, I'm only touching 100,000 of them. So I'm going to be behaving the same as if I only had 100,000 examples. Right? So here this term would be maybe very small, but it doesn't matter because this term would be the dominant term, which would be the same as here. Okay? The other option is to do many more than 1,000,000 examples. So if I did 100,000,000 examples, I'd really make this term very, very, very small. But it doesn't matter because the dominant term would be this one, which would be dominated by the number of examples. Okay. Let me actually skip this because I want to get to the. Okay. So it seems though, okay, so back. Okay. So what we said is that the control, the complexity control, the knob is in the step size, but we're still not seeing where the regularization comes in. After all, I chose here a particular regularizer, the Euclidean regularizer, and here it's very clear, a particular complexity control, where the complexity control is coming in. I'm limiting myself only to predictor with small Euclidean norm. Where is the regularization coming in for the direct approach? Okay? And so in order to see that, we have to think about what is it that actually stochastic gradient descent is doing. Okay? And so, let me skip this. Okay. So how stochastic gradient descent is operating? So even think about gradient descent for simplicity. So at each iteration, what gradient descent is doing is thinking about it as subtracting the gradient is actually kind of a wrong thing. Okay, so if you think about what is a gradient, right? A gradient is a point. I mean, the way I view it, a gradient is a linear functional on the. The gradient defines a linear approximation of your function. Okay, so it's a linear functional. In some sense, it lives in a dual space to your data, right? If your data, if you're thinking of the x's or think of the w's as column vectors, then the gradients are linear operators of the column vectors. The gradients are row vectors. Okay? And so just saying that you're taking a gradient and you're adding it to w is like adding a row vector to a column vector. And it should be wrong. You can't just add, you can't go about adding gradients which are linear functionals to the points themselves. So maybe the better way to look at gradient descent is this way. So what you're doing at each step of gradient descent is you're looking at a linear approximation to your function. And you're saying, okay, let's, instead of minimizing the real objective, which is f, let's minimize its linear approximation, okay, which is given by the gradient. Okay. The problem with this is what happens if I minimize the linear approximation? What's going to be the minimum of this linear approximation? It's going to be way down here. Okay? And this is not good, right? Because, well, first of all, way down here, this approximation is not valid. And the second, also, if I have stochasticity, I don't want to really be jumping around like, all the time like crazy, right? I do want to kind of remain local. And so what we do at each step of gradient descent is we minimize this first order approximation plus a proximity term that says that we have to stay close to our previous iterate. Okay? So which is given by this proximity term with a coefficient that I called here 1 over eta times the, oops, there's a squared missing here. There should be the squared L2 distance between a point, between the point W and the previous iterate. Okay? And now we're optimizing here with respect to W. This is just a linear function of W. This is a quadratic function of W. We can solve it in closed form. And what we get is exactly this, the familiar gradient descent update. Okay, okay. So here's two things. One is we maybe resolve this problem of like, why are we suddenly adding a row vector to a column vector, which we'll get back to again. But the second is now maybe we see more explicitly where the Euclidean regularization is coming in. Okay, so we now see very explicitly that the way we're kind of requiring things to not change too much is using this squared Euclidean term. Okay, okay. So in order to be able to both understand how this is actually ensuring generalization and be able to generalize to other norms, we have to think of what is this term doing. So forget about stochastic gradient descent written this way. Think about stochastic gradient descent written this way. And the way we can, the key that we'll use to understanding it is through stability. Okay? So let's take a step back, and we'll get back to stochastic gradient descent in about 10 minutes, and talk a bit about stability and generalization. Okay? So if we have a learning rule, so a learning rule is just a mapping from our data to a predictor. So in our case, a predictor, we're going to look at, again, follow Nemirovsky's approach, and our predictors are always vectors in some normed vector space. Okay? So it's a mapping from our data, Z1 through Zm, to a vector. We say that this learning rule is stable. Formally, there are many slightly different notions of stability. This is a leave one out uniform notion of stability. If the following holds, if I look at what happens if I measure how good the result of my learning rule is to one of the points in the sample, if I remove that point from the sample, it shouldn't change much how good the predictor is. Right? So removing one point of the sample doesn't change the loss. And remember that our f is our objective here. It's going to be our loss, the loss on that point. Okay, so this is kind of a natural notion of stability, right? You'd expect that if, you'd hope that maybe changing the sample just by 1 point doesn't change the answer by much. Okay? But what we can see from here is this definition almost directly tells us that if a learning rule that's stable is also going to generalize well. Okay? Because over here, we're looking at how well does the learning rule do on the sample itself. Right? So this is, if we average this over points in the sample, we get the training error essentially. Okay? And over here, we're asking how well does the learning rule do on the point that's actually independent of the points in the sample. So we're taking all the zi's to be independent. Okay? And so this notion of stability directly implies a generalization property. If we have a learning rule that is stable, then now the expectations here are always over the choice of IID sample Z1 through Zm. And we can say that the population error, the expected objective of the learning rule, differs from its empirical error only by beta, by the stability parameter. Okay?
What is the condition on the symmetry?
Okay, so I'm assuming here, we're only going to, the symmetry means that the rule is symmetric with respect to all the zi's. Okay, so if you permute your training set, you get the same learning rule. It's not strictly necessary. I mostly wrote this here to avoid some notation. Otherwise, I would have had to say that I'm stable with respect to any point in the sample that I change, and I just wanted to write it with respect to the last one. Okay, right, yeah.
So perfect interpolators will be unstable?
In general, yes, right? So the only way a perfect interpolator might be stable, so it's very hard at least for a perfect interpolator to be stable. If you have a strongly convex objective and you have some strong, so I can concoct an example in which a perfect interpolator would be stable, right? So if you have a strongly convex realizable problem, okay, then you can have both stability and uniform and be an interpolator, right? Because if you even if you look at a held out point, the error in it will be pretty small. Okay? But that's a pretty rare situation. So in fact, as was pointed out here, in general, we would not expect something that actually gets that minimizing the error to be stable. Okay? And exactly for this reason, what we're going to do to get okay, sorry, let me back up a second and get back to your question in a second. So in some sense, we want to find stable rules, right? If stable rules are going to generalize. Okay, they're not exactly necessarily going to have small expected error. It's very easy to have a stable rule, right? So a trivial example of a stable rule, if I always return 0, right? Whatever data I have, I return the null predictor. that's going to be very stable, right? Because if I change the training set, if I remove an example from my training set, it doesn't actually change my rule at all. But that's a pretty bad rule. It's going to be stable, so this is going to hold. The problem is the empirical error for that rule is going to be very, very, very bad. Okay? On the other hand, as was pointed out here, if I have a rule that really, tries to interpolate the data and get zero error in the data, even if it's not possible to get population error, is going to keep the empirical error very small, but it's going to be probably very unstable. So in some sense, the name of the game here is to get rules that both have small empirical error and are stable. Okay? That both of these terms will be stable. And the way we're going to do it is we're going to introduce the regularizer. And the main property we're going to need for the regularizer is strong convexity. So we're going to say that a function psi over, remember we're living always over our normed vector space, a function psi that maps vectors to the reals is alpha strongly convex if the following holds for any, draw this here, okay, that for any w in w prime, okay, if I look at the function psi at w prime, okay, then it's greater than the linear approximation about w. So this is these first two terms. Okay. Okay. So far, the first two terms just say they're convex, right? A function is convex if it's always greater than its linear approximation. But not only do I want it to be convex, I want it to be bigger by this term that scales with the distance between w and w prime. Okay? So what you should have in your mind, the simplest example maybe for a strongly convex function is the squared Euclidean norm is strongly convex with respect to the Euclidean norm itself. Okay? And the important thing here is when we're talking about strong convexity, so convexity is not a property that depends on the norm. Okay? All I need is a vector space. I don't need a norm vector space, and I can talk about convexity. Okay? Because convexity just involves the first two terms here. And strong convexity is a property that depends on the choice of norm. Right? Because when I say the function is strongly convex, I want to say that as I get further away, as w prime gets further away from w, then I'm gonna be larger and larger than this linear approximation. And so I have to measure what does it mean to get further away. Okay, so the choice of norm comes in here. Okay. Okay. So I'm actually familiar. How many people have seen strong convexity before, or with respect to? Oh, okay, everybody. Why am I spending so much time on it? Action. Okay. Okay. And the important thing is that strong convexity directly. Okay. Oops. Maybe the one property I want to mention is that for a strongly convex function, okay, if w naught is the minimizer of psi, then for any other point w, I can lower bound the value of psi in terms of its distance from w naught. Okay? So if I move away from w naught, the value of psi increases proportional to the square of how far I move away. And in some sense, this property is what's going to give us stability. Because if our objective now, our learning rule is going to involve minimizing some strongly convex objective, right, then as I in order to moving very far away would mean that the value of our objective changes by a lot. And so if a data point only changes the objective by a bit, it's not going to be able to move the minimizer by a lot. Okay? And I'm not going to prove this here. There will be, I think, the lecture notes will include full proofs, and I can also send you, if you're interested, before lecture notes references. This is not too difficult to prove, but the sort of main result is here is that strong convexity implies stability. Okay, so to state that, we have to be a bit more careful. So the learning rule we look at is instead of just minimizing the empirical error. Okay, so we switched here from L to F because we're talking about a general stochastic optimization problem. So this is the empirical average of the objective. Instead of just minimizing it, we're going to minimizing it plus the strongly convex regularizer. Okay? And in order to establish stability, we need one more thing. We need to say that we need to bound how much changing the predictor changes the objective value. And so for that, we're going to need a Lipschitz property. So we're going to need to also assume that our objective is Lipschitz with respect to the same norm. So again, what does it mean to be Lipschitz? It means exactly what we said now. We're bounding how much does the function change, the objective value change, when we change the predictor. Okay? And again, this depends on the choice of norm. Right? Because we're looking at how much does the function change as I change in a particular norm. And the important thing here is we can choose any norm here, but we're going to have to use the same norm for our measuring the strong convexity and for measuring how fast our objective changes. Okay? And another way to think of the Lipschitz constant, so Lipschitz with respect to L2, standard Lipschitz, correspond to bounding the Euclidean norm of the gradient. If I'm talking about Lipschitz with respect to some other norm, then now this corresponds to bounding the gradient in the dual norm to the norm with which I'm talking about Lipschitzness. Okay? So I don't know if it's whichever is easier for you to think about how things change when they change W by some norm, or think about the dual norm of the gradient. Okay. So if indeed I have a regularizer that's strongly convex and the objective is Lipschitz, then regularized ERM now is stable with parameter that depends on the Lipschitz constant of my objective, the amount of regularization I added, the strong convexity parameter of my regularizer, and scales as 1 over the number of examples. Okay? And I should say that here I'm still including the regularization parameter, but I can the parameter of strong convexity. I can of course change the parameter of strong convexity just by multiplying my regularizer by a constant, which is exactly what I'm doing here anyway. And so without loss of generality, I can always rescale my regularizer to be 1 strongly convex, and to take this alpha to be 1. And so I think in later derivations, we'll just drop this alpha from here and assume our regularizer is 1 strongly convex. Okay. Okay. So we said that regularized ERM is stable. How do we actually learn with it? We said in order to learn, we need to have a rule that on one hand is stable, and on the other hand actually gets small empirical error. Okay. And let's see what we get with the regularized ERM. And so the problem here is we're not actually minimizing the actual empirical error. We're only minimizing the regularized empirical error. So we have to account now for two things, both for this additional stability term and for how far are we from actually minimizing the empirical loss. So this derivation I actually want to go through because I think it's useful for understanding this balance. And so what we want to bound is the population error of the result of our regularized empirical risk minimization learning rule. And based on stability, I can decompose it to the empirical error. And the expectation here is over the sample plus the stability term. Okay? And what can I say about the empirical error of the regularized empirical risk minimizer? So at least if my regularizer is not negative, and again, I can take that without loss of generality because otherwise I'll just add a constant to it to make it not negative. And adding a constant to psi doesn't actually change the learning rule. Then I can bound the empirical error of the regularized risk minimizer by its empirical error plus this non-negative regularization term. And now I know that my regularized empirical risk minimizer actually minimizes exactly the sum of both of these terms. Okay? And so, so I know that the empirical error plus the regularizer value of the empirical risk minimizer, oops, this, I really apologize. I will try to fix the slide later. Note this W should be, again, the regularized empirical risk minimizer. I'm adding here, should be adding psi times the lambda times psi of the result of the regularized empirical risk minimizer. Okay? And now I can say that since the regularized empirical regularizer is exactly chosen to minimize the sum of these two terms, it's going to be less than or equal to this objective applied to any other predictor, W. Okay? And now, in particular, and now I get this holds for any W, including the W that minimizes the population loss. And I see I have here exactly these two terms that I need to control, the lambda controls. In some sense, this is the approximation term, right? So this term, lambda times psi applied to W, is the additional empirical error I'm going to get from the fact that I'm only minimizing the regularized empirical error. So as lambda is going to be bigger, I'm introducing more regularization, I'm going to be, my empirical error is going to be higher and higher. And this is going to be accounted for this term. On the other hand, here I have a term that scales as 1 over lambda and controls the stability. Right? As if I'm adding less and less regularizer, then I'm going to be, my objective is going to be less and less strongly convex. I might be jumping around and I'm going to be less stable. And I need to balance these two terms. And at least if I want to, if I know what the supremum of this regularizer value is, the optimal balance can easily be calculated. And plugging that in, I get an error term here, which depends on the value of the regularizer on the W's with which I want to compete, times the Lipschitz constant divided by the number of samples. Okay, okay, so let's see what's going on here. Let's try to understand this term. So really, this is going to be a bound on our suboptimality. I mean, we're going to find a predictor and we're going to measure its population loss and compare it to the best in the class, okay, the predictor we want to compete with. And we see here that we depend on two terms. On one hand, on what is we should think of this regularizer as a complexity. What is the complexity measured according to this regularizer of the predictor we want to compete with? And the Lipschitz constant, which I'm now writing here, is just the dual norm of the gradients. Okay? And so in particular, what we can think about is this method of adding a regularizer term allows us to solve problems that are convex Lipschitz bounded. Okay? So first of all this applies only to convex problems. For the regularized ERM to be convex, and yet a strongly convex regularizer, but I need the objective itself to be convex. I need to be able to bound the norms of the gradient, I need to be able to bound the norm of the gradient under the dual norm of the norm I chose. And I need the predictors I'm going to compete here to be bounded in terms of psi. Okay? And psi has to be strongly convex. Okay? So let's just think of how this looks like, how this Lipschitz condition looks like, the convexity in Lipschitz condition looks like for supervised learning problems. So let's go back to supervised learning. In supervised learning, up until now, we talked about general objectives. For a second, we're going to go back to supervised learning problems, in particular to linear learning problems of this form, where the prediction is just W times some feature map of X. Okay? And in this case, how do we ensure convexity and Lipschitzness? So convexity comes directly from the convexity of the loss. If my loss as a scalar function is convex, then my objective function for this generalized linear problem is going to be convex. Okay? I do also want to point out that if I want my objective to be convex, okay, my objective here, f, to be convex, the only way to achieve it in some sense is to look at a generalized linear problem. Right? So, right, so if your objective is of the form that it's the loss of some predictor parameterized by W against the label Y, then at least if this loss is non-degenerate. Okay, so for simplicity, think of the loss just being an absolute loss, although this work also work for a hinge loss, or really any loss that's sometimes increasing and sometimes decreasing. Then you need the objective function. So this objective function, you want this to be convex with respect to W. How can it be convex with respect to W? Okay? So if your loss is non-trivial, then sometimes the loss is going to be increasing with h of W. If the loss is increasing with h of W, then in order for the loss to be convex, you need h to W to be a convex function of W. Other times, your loss is going to be decreasing with HW, right? Because sometimes you want to, sometimes you're gonna, depending on the label, if the loss is non-trivial, depending on the label, you want to either to increase or decrease your predictions. If your loss is decreasing with HW, okay, then that means that HW has to be a concave function of W in order for the loss to be a convex function of W. So for the objective to be a convex function of W, then the prediction HW has to be both a convex function of W and a concave function of W. And so the only option for it is to be a linear function of W. Okay? So when we're talking here all the time about convex optimization problems, convex stochastic optimization problems, it's important to keep in mind that if we're talking about learning, we're only talking about linear learning problems. Okay, when we say linear, it's linear in W, right? It can still depend on arbitrary mapping of X, that doesn't matter, but it can handle kernel problems and so forth, but only linear in terms of W. Okay, so that's the convexity. What about the Lipschitzness? So just applying chain rule, right? I want to bound the gradients of F. It's going to correspond to the derivative of the loss times the gradient inside here, which is this phi of X. Here you can see it directly from the Lipschitz property. And so in order to bound the Lipschitz constant for our objective with respect to W, our objective, we can bound the Lipschitz constant of the scalar loss. That will generally take to be, say, 1. That would be the case for the logistic loss or the absolute value loss or the hinge loss. And more importantly, the norm of the phi of X, the norm of the data, measured under this dual norm. Okay? So the Lipschitz's property corresponds to some bound in the norm of the data. Okay? And so the guarantee you get then depends on this regularizer applied to the predictors you want to compete with, times the bound in the norm of the data, okay, the dual norm of the data. So now, what's the game here? So we have some learning problem, okay, and what we can pick is we can pick which norm in which regularizer we want to work with. Okay, that's the regularizer is going to determine our learning rule, and we want to pick them in a way that makes both of these terms small. Right? That we want to pick some norms such that the data is bounded in the dual norm, and at the same time that allows us to have a regularizer psi that's strongly convex with respect to that norm, and where we believe our predictor is small under that regularizer. Okay, and so the picture you should have is roughly like this. I have some assumption about my data, right? So my data lies maybe inside some space here. You can think of this as the gradients of the objective, which is, as we said, the same for a supervised learning problem, the same as the data. Okay, and I have maybe some belief about what type of W's I want to compete with, right? Okay? And now I have to choose a norm such that the norm ball, the norm ball for the dual norm capturing all the data is going to be as small as possible, right? So I'm going to have, I'm going to suffer from looseness here if this is too big, okay? And at the same time, a corresponding strongly convex objective, which is, or a strongly convex regularizer, which is strongly convex with respect to that norm, that's small on the W's that I expect. Okay, so maybe we'll see some examples and see how this plays out. So the simplest example is to choose is our norm, the Euclidean norm, and is our strongly convex regularizer is the squared Euclidean norm. Okay, and in that case, the enumerator here, which would correspond to our sample complexity, would just correspond to the squared norm of the data. Oops, I think I dropped the phis here. Okay, the squared Euclidean norm of the data times the square Euclidean norm of the predictors we want to compete with. Right, so this would be fine if we think our predictors have small Euclidean norm and the data has small Euclidean norm. Okay, does this make sense? Okay. But now maybe our data is not actually bounded in the Euclidean norm, or maybe alternatively, we don't expect our predictors to have small Euclidean norm. We expect them to have some other norm. Okay? And so one maybe easy choice to understand is if instead of looking at the Euclidean norm, we look at some other quadratic norm. Okay? And so if you look at some other quadratic norm, then we can choose. So if we look at a quadratic norm given by some positive semi-definite matrix Q, then this is basically the same as Euclidean norm after some change after a change of basis. And again, I can define the square of that norm would always be strongly convex with respect to this norm. But now, if I look at my guarantees, what I get is the norm of my Q norm of the predictor times the dual norm here, which corresponds to the Q inverse norm. Okay, the norm measured under the inverse quadratic term. So you can see that I have flexibility in choosing which norm I work with, which regularizer. That would change sort of my complexity. You can think of it here as changing kind of the geometry of the problem. But if I shrink it, if I in some direction, if I try to shrink Q because I think maybe W is very wide in that direction, I'm going to pay for it when I look at the data. Right? So I always have to balance both of these terms. Another example is going to, instead of the Euclidean norm, I can go to LP regularizers. So now the LP norm is dual to the LQ norm. So for any P, I can choose as my norm the LP norm. And then as a to get a strongly convex regularizer, I look at the squared LP norm, but with a p-factor of 1 over p minus 1. So this only works for p strictly greater than 1. Okay? And in that case, my sample complexity is going to depend on the p norm of my predictor and the q norm of the data. So again, I always have to kind of measure the complexity of the data and the complexity of the predictors are going to be dual to each other. Okay? The problem is this is going to explode as p goes close to 1, which is unfortunate because that's frequently what I want. Okay, so why do I want to take p close to 1? So one thing you can think about it is that I think that maybe my W is sparse, and so it has small L1 norm. But really, that's not in some sense the real reason, because measuring the L2 norm is always going to be better than the L1 norm. Right? The L2 norm is always less than or equal to the L1 norm. So I actually don't, in terms of the LP norm of W, I never win by taking B smaller and smaller. The real reason I want to take P smaller than 1 is because I'm also looking at the LQ norm of the data. Okay? And so the L2 norm of the data is going to increase with the dimensionality. Right? So the squared L2 norm can increase linearly with dimensionality if all the coordinates are the same magnitude. Really what I want to do is take P to 1 so that I can take Q to infinity and only pay for the L infinity norm of the data. Right? And then I only depend on the maximum value at each coordinate rather than the number of coordinates. Okay? So I cannot do that by taking the L1 norm squared is not actually strongly convex with respect to L1 norm. But I can do that by taking a different strongly convex regularizer, and this is this entropic regularizer. So this entropic regularizer is one strongly convex with respect to the L1 norm, is written here, at least that holds when the L1 norm is bounded. And now you depend, with this choice of regularizer, you can choose the L1 norm as your norm, and you pay for the L infinity norm of the data, which is what we wanted, times the L1 norm of W, which we're willing to suffer if for that we need to assume that our predictor, for example, is sparse, and we can suffer that. And an additional log term here, which comes from the entropy. In fact, we have to normalize the entropy here to ensure that our predictor is non-negative. Okay, so as we see here, we're already seeing that we're kind of like choosing a geometry. We have to choose the geometry of the regularizer based on kind of the geometry both we expect of the data and of the predictors. Okay, but all this we didn't yet talk at all about optimization. All this was just on for learning rules, for these regularized empirical risk minimization learning rules, and we didn't say how we actually optimize them. Really what we want to get at, and I'm seeing I don't have much time, so, really what we want to get at is think about stochastic gradient is optimization algorithm. So we already said that stochastic gradient descent in some sense has this Euclidean norm, and again I'm missing the squared here, as the squared Euclidean distance is an effective regularizer each step. So really what we want to do is we want to understand if I have a general regularizer that captures kind of my the global geometry of the problem that I'm trying to capture, what's the stochastic approximation algorithm that corresponds to it? Okay? Is this question clear? So this is kind of what we've been working up towards. So in order to do that, really we're interested in stochastic optimization, but we'll take a slight detour through online learning. So in the online learning problem, in some sense captures some of the mechanic of stochastic approximation when online learning. How many of you have seen the online learning setup before? Okay. Or maybe I should ask how many have not, so I know how much. Okay, nobody. I see raise your hand. Good. So I'm not gonna good. So I don't have to spend time in it, but you're right. We see each time as a learner, I receive each time I need to make a prediction, and then I see. Before seeing any data, I already have to make some prediction. I receive Z1, I see Z1. I suffer the loss of using my predictor on Z1. Based on that, I can update my predictor W2. I see Z2 suffer the corresponding loss. And again, I can update my predictor W3 and so forth. So each time, I have to choose a predictor only based on what I've seen so far. And the loss I suffer then is the loss each time of predicting on Zi based on just the previous samples. And the online regret is defined as the suboptimality versus the best I could have done if I just used some single predictor chosen in hindsight on everything. Okay? So the online formalization here doesn't have any stochasticity, any randomness. There's nothing stochastic here, and it can be applicable in many settings where you do not want to assume that something comes, as IID or stationary. The way we're going to use it here is just to argue that if you have small online regret, then just by taking expectation on both sides, then you can transform a online regret to a stochastic suboptimality. Okay, so maybe actually, since I don't have much time, I'm going to skip this derivation. But you basically just take expectation on both sides, and we see that if an algorithm with bounded online regret, it also bounds its suboptimality. So while we go to online learning, so let's think of what stability gives us for online learning. Okay, so what I claim is also here what we want to get is stability. Okay, so we're going to use the same notion of stability. And the equivalent for the empirical risk minimization learning rule is the follow the leader learning rule. So follow the leader basically just says do ERM at every step. At every step, predict the thing that's best on everything you saw so far. Okay? Okay. So using stability, we'll compare. So this rule, I know, could be good, could be bad. It could be very bad because if, for example, I have a linear loss and my data keeps shifting from one side to each other, my prediction is always also going to jump from one side to the other based on each time, kind of, what did I see more, plus ones or minus one, and I'm going to be sort of always incorrect. And the problem here is, again, because the reason I'm always incorrect is because I'm very unstable. So the way we're going to use stability here is we're going to compare the follow the leader learning rule to a much better but unfortunately unimplementable learning rule, which I call be the leader. So follow the leader looks at what was the best in all the examples so far. And be the leader looks at what's the best in all the examples so far, plus the following example that you haven't seen yet. Right? So you can't actually implement this be the leader learning rule. Right? But stability tells us that follow the leader, so be the leader is an excellent learning rule. In fact, be the leader always has non-negative regret, right? It's always at least as good at choosing the best single thing in hindsight, right? It's super powerful. And stability tells us that be the leader and follow the leader are pretty similar. So in particular, we can bound the regret of follow the leader in terms of the regret of be the leader, which is non-negative, plus the sum of our, now instead of talking about a single stability at each step, I have a different number, for example, so the sum of my stabilities. And so, again, what we're going to want to do is something like follow the leader, but in a stable way. And so what we're going to do is instead of follow the leader, follow the regularized leader. Okay? And it's exactly the same idea from before. We add a regularization term each time, and we minimize the best and everything so far plus a regularization term. Okay? In the guarantee we can get there, for the online regret guarantee we can get for follow the regularized leader is exactly of the same form that we had before. Okay? It's going to correspond to the regularization term. We have to choose a psi and a norm. Oops, and there's a dual norm missing here. We're going to have to choose a psi and a norm. And we're going to pay the dual norm of the gradients, the dual norm applied to the data, and psi, exactly like before. Okay? So we can already see how to use some general strongly convex regularizer to get an online learning rule. The problem is that this online learning rule really does not look like a stochastic approximation algorithm. It's follow the regularized leader, right? So remember, calling in stochastic approximation algorithm. The stochastic approximation algorithm, like SGD. What I wanted to do, I'm finished. I'll wrap up in like 5 minutes or so. So in stochastic gradient descent, what we want to do is each time I have an iterate, I use just a single point to do a simple to calculate update on this iterate, right? So this is what I'm doing here. I have my iterate WT. I'm written here as solving a minimization problem, but really this minimization problem is just a simple quadratic minimization problem that I can solve explicitly. I only need to use the current iterate and the current data point. That's it. Okay? Right? And whereas what I'm doing here, at each step, I'm actually solving an entire optimization problem. So this doesn't, not only I need access to the entire objective over all the data points and to solve this problem, it's like solving an empirical risk minimization problem all over again. So this doesn't actually help me. So how do we get from this to something that does look like stochastic gradient descent? So we have to take two steps here. The first one, you're going to have to take on faith, and I'm not going to do a derivation. But the idea is that for a convex objective, I can actually, when I look at for the leader, I can replace each objective, but it's by its linearization about the iterate at which it was, at which it came. Okay? And this.
So here is WIZI.
Sorry, this is WIZI. Thank you. Thanks for the correction. That's important. This is WIZI, right? So each time I take I look at the linear for each ZI, I measure it against the linearization at the about the WI in which it was obtained. And roughly speaking, this comes from the fact that a convex objective is always lower bounded by its linear approximation, and so this the linearized follow the leader is always at least as good as follow the regularized leader. So this already gets us somewhere because we already see that we don't need full access to F. We only need access to the gradients we had so far. So all I have to keep track of is not the points, but just all these gradients. Okay? So I already have kind of a gradient-based method, which is good. But still, at every iteration, I'm solving and this optimization problem is not so bad. This is just a linear function of W. Okay? So each iteration, I'm just solving minimizing something which is a linear function of W plus psi, similar to what we did here. Okay? So this is already much better, but it still seems strange because I'm not just using the last iterate. I still need to kind of keep track of everything I had so far. And the second step here, which we will see in a bit more detail next time, is that this linear follow the regularized leader can also be implemented in the following form, which is each time I just minimize the linearized loss against for the current iterate. Okay, so just the current linearization, just like here, plus a divergence term. So that generalizes the divergence term we had here. So the squared Euclidean distance is a divergence term with respect to the L2 norm. And what we're going to define is a general for any strongly convex regularizer, a corresponding divergence, which is going to be the Bergeron divergence. Okay? In particular, we'll define the Bergeron divergence on the next slide, but for the Euclidean norm, we'll see that the Bergeron divergence with respect to the Euclidean norm is just this squared Euclidean distance that we have here. Okay? So this is going to be, so these updates, which we'll refer to as mirror descent updates, is going to be are going to be our generalizations for gradient descent for a generic strongly convex regularizer. So it's just before we finish for today. Is this okay or? Oh, sorry. Okay. So so let's try to understand this Bergeron divergence that plays such a role here. So we have a strongly convex regularizer psi. The Bergeron divergence between 2 points looks at the difference between psi at point x and the linear approximation in the value at x of the linear approximation of psi about y. Okay? So I take, right, for any 2 points x and y, I take a linear approximation about y and see how well it, how poorly rather it approximates the actual function at x. So recall that our regularizer is always, well, it's always convex. It always means that it's always going to be lie above any linear approximation. It's also strongly convex. Okay, so the fact that it's strongly convex means that it's going to be strictly above this. Not only strictly above this, but that the Bergeron divergence is going to be strong convexity. Exactly means that the Bergeron divergence is lower bounded by the different distance between x and y, measured by the appropriate norm. Okay? And this turns out to be the right notion of divergence. Okay? So let's just try to see. So okay, I'll take maybe a few more minutes just to try to understand maybe more intuitively what's going on here. So we define mirror descent as this generalization of stochastic gradient descent, which at each step I minimize a linear approximation plus some divergence term that's going to capture kind of how close, in what sense do I want to stay close to my current point. Okay? We can think of it also in another way, so we can we can try to solve this. So for gradient descent, we said that what we get is a quadratic approximation problem. Sorry, we just get a quadratic objective, and we can actually minimize it in closed form. We can do the same here. So let's just minimize this objective with respect to w. So we'll take the gradient of the objective that's written here, the argmin with respect to w, and set it to 0. Okay. So what's the gradient with respect to w? So the gradient with respect to w of the first term is just the gradient of our objective at wt, gradient of f wt zt. And the gradient with respect to the second term, we'll plug in the definition for Bergeron divergence. So, and we want to take a gradient only with respect to w, which is confusingly w prime in the way I wrote it here. So it's going to be the gradient of psi at w. This is going to be psi of wt. It doesn't depend on w. Plus this is psi wt times the difference in w and wt. So you have here plus. It should be minus, I think. No? Oh yeah, it is minus. I have a minus from here. Minus psi of wt. Okay? And we want to solve this for w. Okay? So how can we solve this for w? So to solve this for w, we can write that psi of w, the gradient of psi of w is equal to the gradient of psi at wt minus this gradient. And now we have to hope that the gradient of psi is invertible, which it would be if psi is strongly convex, because and we can write that what we get here is the inverse of the gradient applied to that expression. Okay? And there's one more thing that I rather ignore at the moment. The optimization is only over some constraints at w, but we'll soon relax that. Anyway, if it is, then in the end we also have to project back to that W. But for now, let's just ignore this projection. So the way to view this, and this is actually the original way that Nemirovsky, I think, developed mirror descent and how it's got the name, like where the mirror comes in. What happens is we start at a point in we start at some point, it's not here, in our primal space, in the space of so B is the, think of it as the vector space or Banach space containing our optimization variable W. Okay? So we start at some point W here. And we want to add a gradient to it, or rather subtract a gradient. But as we said, we cannot subtract a gradient. The gradient lives in the dual space. Right? So the gradients live over here and the iterates live over here. So what we're going to do is we're going to map the point, our current iterate, to the dual space. And you can think of this gradient of psi as a link function that maps from the primal space of iterates to the dual space. Once we're in the dual space, here we can now add the gradient, or rather subtract the gradient. Okay? And then we're going to use the inverse link function to map back to the primal space. Okay? And then finally maybe also project back. Okay? And so the choice of regularizer psi corresponds to a choice of the mapping from the primal space to the dual space. Okay? So if we think back for the to the Euclidean case, the psi was just the Euclidean norm squared. The derivative is just the identity. Okay? And so these link functions are just the identity, the forward link function. But what's the identity? It's not really the identity. It's identity just when we write things as a vector, as an array of numbers, right? The identity it is still a specific mapping that's depending on the choice of basis between the primal space and the dual space. If we chose, for example, a different basis, then our standard Euclidean norm would be different, and that would correspond to a different mapping between the primal space and the dual space. And what we're allowing here is not just linear mappings between the primal space and the dual space, but arbitrary mappings between the primal space and the dual space. Okay? Let me just finish this. Actually, I will not finish this slide. Let me return to this slide. So we'll finish next time. So this is summarize where we got. We almost got to where I wanted. And as I said, part of the reason that we talked so much about stability and strong convexity is in order to understand mirror descent. We saw so far two ways of understanding. Maybe I will actually just go to here for completeness. Okay, sorry. Maybe I will finish this. So if you forget the projection for a second, so think of that we don't have actually a constraint in W, we're allowing our entire space, we don't have that projection, then what we're doing each time is mapping to here, adding a gradient, mapping back. Then we're going to map here, back to this point, add the gradient and map back. So all we're doing is, in the dual space, we're just accumulating these gradients. So in the same way that for gradient descent, your iterate is always going to be a sum of gradients, what's happened for in mirror descent is that in the dual space, you just have a sum of gradients. Okay? But each time to figure out at what point you need to calculate the gradient, you have to go back to the primal space. So each primal iterate is a mapping, an inverse link function mapping of the sum of the gradients in the dual space. Okay? And this is just the initial point. If you just take the initial point so that it corresponds to the origin in the dual space, so that the minimizer of your regularizer, which is a reasonable choice, right? We talked also last time. You frequently want to start the optimization from the kind of the simplest model. If you think of psi as your complexity measure, the simplest model is the minimizer, and so the gradient is 0. Okay? This term drops, and you just get that each iterate is the inverse link applied to the sum of gradients, which by the reverse of the argument we had here is exactly the minimizer of the sum of gradients plus the potential function or the regularizer, which was, if you recall, this was the regularized for the linearized for the regularized later. Okay, so what we see here, I still didn't prove you why we're allowed to linearize, but still, if you believe me that we're allowed to linearize, then we see that this procedure where we minimize this linear objective is equivalent to this mirror descent, this incremental mirror descent objective. So we so far saw maybe 3 different or 2 different ways to think about mirror descent. Again, next time we'll continue. We'll see 2 more ways that hopefully might be also more intuitive. One way is in terms of this a link between the dual space and the primal space. In this way, again, is the way it was actually chosen, but to me seems the least transparent. Maybe some of you will give me better intuition. To me, it's least transparent because I don't immediately see how this link function corresponds to like what I think about reality or what my geometry is, or what am I really searching over. Okay? The other way is maybe through this last line here. This is equivalent to doing trying to solve this regularized minimization problem all the time, and then I more directly see how this psi that controls the choice of divergence actually controls kind of my regularizer, that I want to always stay small in terms of psi. Okay? Again, we'll return to this next time, and we'll talk about 2 other ways of understanding mirror descent. Okay, so we'll continue. Actually, where are we continuing? Later this week. Okay, tomorrow? Excellent. So we'll continue tomorrow. Great. Okay. Yes. Oh, God. Oh, boy. Okay. Oh.